Hi, this is Mrs. Basin, and this is a very quick review of Chapter 15. So what I'm doing here is just going through the concept list that I gave you. It's that list that's on the orange piece of paper, and we're just going to kind of talk through a little bit of each one. So the first one says to describe the concept of equilibrium. So remember to make sure you can tell the difference between equal and constant. So when you have a system at equilibrium, the rates of the forward and the reverse reactions are equal and the concentrations remain constant. So you can see these are three different equilibrium systems, and when they reach the point where both of them have leveled out and they're no longer changing concentration, that is where you have reached equilibrium. And at that point, the rate of the forward reaction and the reverse reaction are equal. So again, the rates are equal at equilibrium, the concentrations are constant. When you set up an equilibrium expression, remember there's two ways to do it. So the first way to set it up as a Kc, and the other way we talked about was to set it up as a Kp. So when you set it up as a Kc, what you're doing is you're notating things as concentrations. So Kc equals products over reactants, and we're raising it to the power of the coefficient. So Kc would be H2O raised to the second power because of the 2 over H2 raised to the second, O2 raised to the first. And remember, when you're doing these, you only include aqueous solutions and gases. You do not include pure solids and pure liquids. So here's the same expression, and now we're going to set it up as a Kp. Same deal, you're still taking the products over reactants. So I'm still taking this over this, but this time the notation is just a little bit different, where I'm using a capital P, and then the subscript is the substance, and I'm raising it to the second power. You can use the parentheses or not, you don't have to. And then P of H2 raised to the second, and then P of O2 raised to the first. So same basic idea, you're just using a little bit different notation. The other thing we talked about was calculate Kp given Kc or Kc given Kp. So this is the equation that you will have to use on the test. So if you're given one of those and asked to find the other, you'll also be given the balanced equation, because the other thing you'll need is the R value, so the ideal gas constant, that's in liter atmosphere per mole Kelvin. Your delta N is your moles of gaseous product minus the moles of reactant, so product minus reactants, just like always. And then T is going to be your temperature, and that has to be in Kelvin, and that's because of the units of R. So remember, when you calculate delta N, if it's a negative number, you leave it in as a negative number. If it's a positive number, you leave it as a positive number. If it's a 0, then that would make this whole thing equal 1, and your Kp would equal Kc, so that's a possibility also. The next one says to describe what dominates at equilibrium given K. So this is where you describe whether equilibrium lies to the right or lies to the left, or it favors the product side or it favors the reactant side. So those are all basically ways to say the same thing. So if your K is greater than 1, then we say it lies to the right or it favors the products. The reason K is greater than 1 is because when we set K up, it's always products over reactants. So if K is greater than 1, that means you have a higher concentration of products, a bigger number on the top of that equation. If it lies to the left, we say it favors reactants, and you're going to have that situation when K is less than 1. And that again is because when you set that up, your denominator is going to be larger, which is going to give you a value less than 1. So if K is greater than 1, it favors the products, which lies to the right. If it's less than 1, it favors the reactants, which lies to the left. The next thing we talked about is how to manipulate K. So given an equation and given a value of K, how does K change when that equation is manipulated? So if the equation is reversed, then we take 1 over K. If we have an equation and we multiply it by some number, let's say we multiply all the coefficients by x, then we raise K to the power of whatever that number is. So if x was 2, we would take K to the second power. And that's how you would manipulate K. If you have multiple step reaction given, like if you have reaction 1 and reaction 2, and it gives you the overall reaction, and you have a K for the first one and a K for the second one, to get the overall, then you would take the first K times the second K. So you take the product of the Ks instead of adding them up like we did with the H's. So again, if you reverse the reaction, you take 1 over K. If you multiply all the coefficients by some number, you raise K to that power. And if you have multiple step reactions, then you take the Ks and you multiply them to get the overall K. The next thing we looked at was heterogeneous versus homogeneous equilibrium. So heterogeneous means the components involved are in different states of matter. Homogeneous means they're in the same state of matter. So this first one, these are all gases, so that would be a homogeneous equilibrium. The next two have solids and gases. Those would be heterogeneous equilibrium systems because they have things that are present in different states. This is also a good reminder if you're doing this and you're setting up the Ks. For this first one, all of those things would be included, but for the second one and the third one, you would not include these solids in your equilibrium expression. So when you're doing K equals, this one here would be CO raised to the second over CO, and this should actually be CO2 raised to the second. So these two, put that little 2 in there, these two would be included, but the tin and the tin oxide would not because those are both solids. All right, calculate K given values of equilibrium. I don't have anything else on this slide, but that would be you set up the K expression, and then you're given all of the values for all the components at equilibrium, and it just says solve for K, so that all you have to do is just plug those values in. This would be using an ICE table, so this is calculate K given at least one equilibrium value. So what you would do with this one is you'd have your initial. If they don't give you an initial, then you put in the 0. Your equilibrium value would be given for one of the substances, so then that would go into this box right here. So you would have to add 1.87 times 10 to the negative third to get from 0 to the equilibrium. Then we would use this to figure out the change. So we would use the stoichiometry, and I'm not going to work this out here, but you would use a stoichiometry where this is twice as much as these, and then these two would be equal because those are both 1s. And then once you have those, then you use the change to get the equilibrium. Then once you have the equilibrium, when you calculate the K value, the equilibrium numbers are the ones that go in to give you the K. So you use whatever they give you first to figure out the change. You use the stoichiometry to get the rest of the change, and then use the change to get the equilibrium, use the equilibrium to solve for K. When you are setting up a reaction quotient, again, the difference between a K and a Q is a K is at equilibrium, Q is any point that's not at equilibrium, and most of the time they're going to call those initial values. When you set up a Q, it's the exact same as setting up an equilibrium, or a K, so you still take products over reactants, so I would still take H2O raised to the second over H2 raised to the second times O2, but the values I would use if I was calculating a Q would be initial values or some values that are not at equilibrium. The K is set up the same way, except the K are solved with equilibrium values. Once you have those, then you can look at the Q compared to the K to predict which direction the reaction is going to go to reach equilibrium. So if those two are equal, like you can see in the middle there, if Q and K are equal, that means it's already at equilibrium. If the K value is greater than Q, then it's going to move towards the right. It's going to move from reactants to products to reach equilibrium. If the Q value is greater than the K value, then it's going to shift to the left or from products back to reactants to reach equilibrium. Le Chatelier's principle was the last thing we talked about, and basically what this says is if you have a system in equilibrium and you apply some disturbance or some stress, like a change in temperature, a change in pressure, you change the concentrations, you add something that's going to react with one of the species that are present, then it will shift to relieve the stress and establish a new equilibrium. So here's just an example, and we did lots of these in lab, so hopefully these are pretty understandable. But if we look at this particular one, if it's exothermic or endothermic, that is also something I would include in the equation. So this particular one is endothermic because heat is on the left. If it were exothermic, then the heat would be on the right over here as a product. And remember, a lot of times that can be given with delta H values. So if a delta H is positive, that means it's endothermic, so heat would be over here. If delta H is negative, that means it's exothermic, so the heat would be over on the other side. So like for this particular one, if I increase the temperature, so if I add more heat, then it would shift to the right. And for this particular one, it would become blue. If I decrease the temperature, if I removed heat, then it would shift back to the left to replace that. If I add something like HCl, which has this Cl in common here, that would increase the concentration of this Cl, which would cause it to shift to the right. If I added more water to this, it would shift to the left to use it up. If I added something that removed the water or took the water out, then it would shift back to the right. So again, think about what are you adding. If you're adding something to something that's already there, it's going to shift away to use it up. If you're removing something from the system, it's going to shift in that direction to replace whatever was taken out. Okay, finally, last two things talk about how different things affect equilibrium. So the catalyst affects equilibrium. All it does is it helps it reach equilibrium faster, but it does not affect the equilibrium constant. So if we look at this graph here, we can see the red is the catalyzed reaction. So you can see at this point it's kind of reaching equilibrium right here where they're starting to level out. The uncatalyzed is this one here, so it's reaching equilibrium. It's taking a little bit longer to reach equilibrium, but if you notice, both of those have the same concentrations at equilibrium. So the catalyzed and uncatalyzed reactions have the same concentration at equilibrium. It's just reached faster for the catalyzed reaction. So it doesn't affect the equilibrium constant, it just affects how fast the equilibrium happens. The other thing that we talked about affecting equilibrium or potentially affect K is a change in temperature. So if you change the temperature, that's going to affect K, and whether it causes K to increase or decrease is going to depend on whether you have an exothermic or endothermic reaction and which direction it's shifting. So again, the only thing that's going to affect the value of K is a change in temperature.